Now, we have talked about discrete probability distributions. However, quite often we have attributes which are not taken from a discrete domain where we have a limited number of values, but quite often we have continuous domains. For example, when we consider numeric values such as the height or weight of a dog, and let's assume we want to distinguish between different races of different breeds of dogs. And what could be a corresponding description? Well, we would have, for example, this Bernardiner. I'm not sure what the English word for that is. And we have descriptions like female Bernardiners have a certain height, and the same is true for the males. So the males are a little bit taller and heavier than the females, as you see indicated here. Oops, still have to switch on the pen. Well, here you see descriptions of the females and the males are a little bit taller and the males are a little bit heavier than the female Bernardiner dogs. And you see some of the attributes like color of the fur and also whether it's short or long. And now let's say we want to classify dogs, and we have now descriptions from a continuous domain. And of course, this could come even at different levels of precision. Like we could say the height would be 83 centimeters, or the height could be 83.81 centimeters. And so we have the challenge then, based on some height or weight descriptions or color descriptions, to determine which breed of a dog we would have. So for this, we need to describe continuous domains. And for this, we can use continuous random variables. And if X is such a continuous random variable, then we use a probability density function to describe this variable. The probability density function represents probabilities not for individual values, but for intervals. So the probability density function, which is to be described with a lowercase p, in contrast to the probability which is described with an uppercase p, it is used to define the probability in intervals. So when the values of a random variable are in this interval between some a and some b, then I can take this probability density and sum up over all this interval with the integral that varies the x. And this gives me a probability which is then in the interval between 0 and 1. And this allows me, or this I can use to represent, for example, this canonical cumulative probability distribution. So this is often described with capital F of y, and f of y means that I'm interested in all the values less than some x, and I start at minus infinity until my y and sum up over the probability density varying the x. And this is nothing else than a particular interval, the interval that is limited by y on the upper side. And of course, as y goes to plus infinity, the f of y goes against 1. The idea is basically I have some probability mass that I distribute over the real line from minus infinity to plus infinity. And if I sum up all this probability density, I end up with exactly a probability mass of 1. Now, there are a number of noteworthy continuous distributions over this real line. One is the uniform continuous distribution over a limited interval. For example, here, the uniform continuous distribution over 0 and 1. And how can we, no, let's go one step back. How could we describe this as a probability density function? Well, it would mean, of course, that this is 0 at all times from minus infinity until 0, then it jumps to 1, then it stays at the value of 1 until 1, and then it continues this probability density function. And when I'm now interested in a particular value, let's say f of 0.5, I have to sum over all the mass assigned from minus infinity to 0 and from 0 to 0.5. Now the area from minus infinity to 0 is an area of 0, and then there comes this area which is 0.5 in this direction and 1 in this direction, and this gives me exactly a value of 0.5. Whereas if I have a value here like 2, I would continue to sum, and again here I would have 0 probability mass distributed. Here I would have another probability mass of 0.5 distributed, so overall f of 2 would have a probability mass of 1 in this uniform continuous distribution. Now, I can also very easily implement this. I can sample from this distribution and return a corresponding number. So sampling is often done when I want to generate observations following a particular distribution. And in this case, if I use Python, I can just use this function random.random. Then this returns to me a floating point number in this range between 0 and 1. And I can also modify the intervals, and then I return a number in that interval. And of course, actually, I could use this Python function in order to program this function by just rearranging the actual output that I give when it's sampled between 0 and 1. Okay, now let's get back to our running example of numeric values. We have here some dogs that are female with certain heights and weights, and we have male dogs with certain heights and weights. And now we have very specific observations. Of course, observations do not come in intervals, they come in actual points. Whether these points are correct or whether I go a little bit wrong is not considered in this kind of model. And what I observe here when I have such numbers is that quite often the majority of observations is around an average value, and then there is a certain spread. And this, of course, is often easily modeled by a one-dimensional Gaussian distribution, also called normal distribution. I have a mean value, and around this value, I have a certain area where most of the values for this particular random variable falls. And when I look here at this function f, and then I look at f of mu, then f of mu would basically start from minus infinity, have no area here, it would slow, or almost no area. Actually, for a normal distribution, it is the case that for every x, it produces a non-zero value. However, the normal distribution goes to 0 very, very quickly on both of its sides, namely it drops exponentially. So if we're somewhere over here, the value is exponentially small as you are away from this average value mu. So you pick up very, very, very little probability mass until you come reasonably close to your mu, where reasonably close means in terms of the standard deviation. And within this area of to a standard deviation, well, one standard deviation around mu, which is then a window of 2, you have most of the probability mass. And this normal distribution or Gaussian distribution is characterized by two parameters only, namely by this mean value, where the peak of the distribution is, and by the variance. The variance is the standard deviation squared. So the standard deviation is, you can see this is a bit like, this is the space around the mu that contains a lot of the probability mass. And for statistical reasons, typically the standard deviation squared is reported, which is the same as the variance, or which goes by the name of variance. And this normal distribution here is described as probability density. And this probability density is described by an exponential difference from the mean value squared. And the width of this here is described in this denominator by this sigma, which is the standard deviation, which squared becomes the variance. And it's inverse exponential, and then we must make sure that when we sum the area from minus infinity to plus infinity, when we compute the integral, that everything adds up to 1. And to ensure this, we don't show this here, we need this normalization factor, which includes again the standard deviation as well as the root squared of 2 times pi. So that's what we have, and we have in particular standard normal distribution, which is the case if mu is 0, so it's centered around the value 0, and it has a standard deviation from 1, and therefore, of course, also a variance of 1. We can generalize that to an n-dimensional Gaussian distribution, which is also called a normal distribution. And this looks almost the same, only that this time these x's and these mu's are vectors. And rather than saying we have directly a square of these, the square is basically realized by taking the difference between them, one's transposed and one's untransposed. And here we have a covariance matrix, which describes how strongly the different vector components are correlated with each other. And the inverse of this covariance matrix is basically what used to be the sigma in the denominator. We have the same constant -0.5 that we had before, and we have a slightly different description of our normalization factor. Now our normal distribution is described by mu, which is a vector in our Euclidean space, and this covariance matrix. And this covariance matrix does not only describe sort of like how large the variance is, it describes the orientation of the variance. So in the two-dimensional space, we could have a mean value at the origin, but then depending on the covariance matrix, we could have a standard deviation which is circular. So where in this circle there would be most mass of the probability distribution, but it could also be an ellipsoidal structure where most of the mass is, or this ellipsoidal structure could also be rotated. Every time what we then have to do is, of course, when we integrate in both directions, in case we have this two-dimensional normal distribution, and we do this both times from minus to plus infinity, we must end up with a value that is 1 for plus, well, for x, y, if x and y go against plus infinity. Okay, now with this, we can use, or we can then model in our classifier, in our Bayesian classifier, also numeric values. So The problem now is we have single observations which are very specific. Our assumption is that we have a certain distribution, and our assumption is that we model the actual distribution by a parametric distribution. Parametric distribution means it's not empirically observed, but we assume that there is a true underlying distribution that would describe the frequency of occurrences if we had infinitely many dogs. And then what we have to do is we have to determine from our actual observations the parametric distribution that best approximates our empirical distribution. And for this, what we do is we do the maximum likelihood estimate. We will still look at maximum likelihood estimates later. But when we have a certain set of observations as we have here, we can estimate the parameters. That means our means and our standard deviations, or the covariance matrix, by the following simple computations. Namely, for a given set of observations, the mean value is simply the sum of all these observations divided by the number of observations. That's very simple. So basically, the average of our values gives us the mean value. And that works in a one-dimensional case where we, for example, just consider height. It works also in a vector space where we have more than one scalar for each observation, where we have a vector of scalars. Again, we then just have the averaging of vectors in the Euclidean space. Now, the variance is computed by taking the difference from this mean value, in general, the difference from the mean vector, and squaring it, summing over these, and dividing by n-1. There are statistical reasons why this is n-1 and not n, but let's not bother with that here. And the standard deviation is just the square root of this variance. Now, in our example, we may then have certain kind of observations. Let's say we have here one kind of observations, and then we try from these individual approximations, compute the mean value and the standard deviation, and we end up with a normal distribution, which might have this shape. And for another class, we might have another shape. So different classes would lead to different shapes of normal distributions. And I think this was a bit closer here to the data I had for my dogs. Now, how can I use these distributions now in order to classify with a Bayesian classifier? What I do here is I'm interested, for example, in classifying into female or male Bernardiner dogs. And if the class is female, I can ask the question, what is the probability if the weight is 67 kilograms? Now, the problem is that the probability is always zero, because in such a continuous domain, the probability for any particular value is zero. We only have probabilities for intervals, right? And the probabilities are always defined for intervals. For example, the interval that is limited by an upper threshold. And well, the probability is then computed by computing the integral from -infinity until this threshold. But the probability for exactly one value is always zero. So what we do is, of course, we have an observation. And what we have to assume, we assume that what we do here in this continuous space is basically to have very small intervals. And the small intervals can be described by saying the weight is 67 kilograms plus some epsilon kilogram. And we are interested in the probability that would arise if we would pick a small interval, let's say 100-gram interval, because that's maybe our scale is not more precise, right? So if I step on my scale at home, it shows me 100-gram accuracy something. Whether that's truly calibrated, it's another question, but let's assume it would be truly calibrated, then it has a precision of 100 gram. And so what we assume here is that we have intervals, and the true value falls into that interval of 67 plus minus epsilon. And if we have such an interval, then this interval, of course, has a non-zero probability. Now, for any kind of value that we consider, we always consider the interval. And we do this in the same way for the same kind of interval sizes. So therefore, what we do is we make the simplifying assumption that when we compare values, for example, we have to compare the small area for the blue distribution against the larger area for the red distribution, we always have here the same kind of epsilon environment around the observed value. And in spite of the fact that we cannot really give a probability for a specific value, since we multiplied with a small epsilon, and we can even assume in a very tiny environment around the true value, there will not be much change of probability density, that we basically compare rectangles. You see, we make a little bit of a mistake here, but we don't care that much about the mistake. So for a new data point with weight 67 and height 155, we have computed parameters for our normal distributions for the female and the male exemplars from our training data set. And we have determined that the mean value of weight for the female was 65.57 and for the male was 6 kilograms more, and that we had a standard deviation of about 2 in both cases. And likewise we do for the height. We have a bit larger values and a bit larger standard deviations. Then we calculate how probable is it to see female or male dogs at all, which you see, you always have to look at your data set, may be wrong. Yeah? It's a small data set, and we have, I would expect that for dogs, there's also approximately 50% chance of seeing a female or a male dog. So it's already a somewhat distorted data set, but that's quite realistic that data sets are not perfect. So we would have a prior category for female of 7 divided by 18 and for male 11 divided by 18. Yeah, priors don't really make sense, but that's the way it is in our data set here. And of course, we could think about readjusting that. There are different means, for example, subselecting only. If we assume that truly we have the same number of females and males, in our dogs in general, we could, for example, assign smaller probabilities of observing such a male, not 11 out of 18, but also just 9 out of 18. We could pick only a smaller subset of these, or sample some of these rows several times. For example, pick that this row and this row appears twice, and we would do this randomly in order to have a equal-sized distribution of female and male dogs. Okay, now for a specific observation, like we are interested in our class female and a specific observation of 155, we would look into our normal distribution and we would look into the probability density function. and that would give us a value, which is not a probability really, but it's would be the probability maybe for a small epsilon environment around that value. And the same is true for the height. And then we include the prior, and then overall we classify our observation to be female by multiplying the prior with these two probabilities and end up in this. Without the prior, that would be like this. And then we do the same for the class male. And again, we have distributions with prior and without prior. And we see with a prior, the male would be much more likely without a prior also. So the prior here wouldn't even change something. Now, what have you seen here? A Bayesian classifier. We describe the Bayesian classifier by the different attributes influencing our target category. And this is the simplest so-called graphical model that you can develop. Not in this winter term, but in the winter term 25-26, I will give the probabilistic machine lecture again. This winter term I plan to have a sabbatical, research sabbatical, so this will not be given. And in this probabilistic machine learning, we describe more general ways of how interdependencies between random variables can be described and how this can be exploited and how causal reasoning can be built on top of that. And graphical models are generally probabilistic models with multiple random variables and dependencies, and they are a general framework for modeling with probabilities for both regression and classification, for both unsupervised and supervised learning. And they're also used for other kind of problems like reinforcement learning or language modeling. This is also some of the research that we currently pursue. For example, here is a much more complicated research that Tim Schneider is doing. He's one of the researchers doing the tutorial lessons, the ones for the engineering researchers. And he does not only describe priors over categories, but also priors over functions. So here we have different functions, and each function is assigned probability, and there are infinitely many functions that are described here. And these kind of priors are used in order to derive functions from individual data observations. And what you here see is then a probability for these functions to take a different shape. This is a function that's less likely, and this is a function that's more likely. And this gives us very good results in the case when you have background knowledge, when you have prior expectations, not only about how often a class appears, but prior expectations about what, for example, is a highly probable function to work with. So thank you very much for